Welcome back to Control System Lectures. In this video, we'll continue our discussion on sketching a Bode plot by hand, with the goal of being able to approximate the frequency response of a system that's represented by a transfer function. It's important to note at this point that we're defining the building blocks of transfer functions. And when these blocks are combined, we can build up larger and more complex transfer functions, but still be able to approximate their frequency response very easily. The four different building blocks that we're discussing are constants, which have no poles or zeros, a polar zero at the origin, a real polar zero not at the origin, and a complex pair of poles or zeros. All transfer functions are made up of some number of these four blocks, so by learning the frequency response of each block individually, it will be a simple matter of summing the responses to get the total system response. In the first video, I showed you what the frequency response was for a constant. And in the second video, we discussed poles and zeros at the origin. And now we're going to take this one step further with real poles and zeros that aren't at the origin. Now there's a distinction I want to make at this point that I think is important. If it doesn't make sense right now, don't worry about it because I'll explain it several more times in slightly different ways in future videos. But when I talk about poles and zeros, I'm referring to the values of the operator s that cause the transfer function to either go to infinity or go to zero. So when I say that we're looking at real poles or zeros, that means that that value of s is a real number. And this number is where the pole exists in the s-plane. And the s-plane can be graphed on a real and imaginary axis, where the real component of s is sigma and the imaginary component is omega. So we can plot s equals -1 on this graph. Now, as you know, to solve for the frequency response of a system, we set the real part of s to 0 and only look at the imaginary part j omega. This means we've confined ourselves to examining the system along this imaginary line only. But even though the pole or zero doesn't lie directly on the imaginary axis, be sure that it is impacting the response along this line. If I draw this in 3D, it might make more sense as to how a pole, in this case, is impacting the surrounding landscape in the s-plane. As you can see here, the j omega line, represented in pink, is impacted by the pole. And as we've seen before, and we'll also see in this video, even though you're confining s to the imaginary line j omega, the response of the system can still have both real and imaginary components. I'll point it out when we get there. Let's start with a single real pole and solve for the frequency response. The transfer function for a real pole can and should be written in this form: 1 over 1 plus s over omega naught. This form makes recognizing the break frequency omega naught easier to do. Also, omega naught is sometimes referred to as the corner frequency. Now, depending on the industry that you're in or the textbook that you're using, they might not actually represent a single real pole in this form. You might also see the same exact transfer function written as omega naught over omega naught plus s, or 1 over 1 plus tau s, where tau is the time constant, which is 1 over omega naught. Now, all three of these representations are equivalent, but I'm going to be referring to this blue representation for the rest of this video. Now, I'm going to warn you at this point that the math coming up might seem intense, but I assure you it's all simple algebraic steps. Plus, it's the same steps that we did in the previous videos. There's just going to be more of them. We first start with the transfer function, and then set s to j omega. And at this point, we're trying to separate the real component from the imaginary component. And we do that by multiplying by the complex conjugate of the denominator, which is just the real part minus the imaginary part. And this is equal to 1 minus j omega over omega naught over 1 plus omega squared over omega naught squared. So you can see from this solution that the real part is just 1 over the denominator, and the imaginary part is minus omega over omega naught over the denominator. At this point, we solve for the gain and phase of this system in the exact same way as we had done in the last video. Namely, that gain is 20 times log base 10 of the magnitude of h of j omega, and this is just the magnitude of h of j omega written in decibels. So at this point, I'm just going to put the real parts and the imaginary parts in and just sort of zip through this algebraic math. I encourage you to try this on your own and go through all of these steps. One, to make sure I didn't make a mistake, and two, I think that just practicing this helps it to sink in and that you'll remember it a little bit better. But at this point we get to 1 over 1 plus omega squared over omega naught squared, and the whole thing square rooted, which is the magnitude of h of j omega. And when we convert this to decibels, this is just negative times 20 log base 10 of the square root of 1 plus omega squared over omega naught squared. The negative came from the fact that this was in the denominator and we moved it to the numerator. And this is just the gain equation, so we can use this to plot the gain on our Bode plot. Phase is a little bit simpler. It's the arctangent of the imaginary part over the real part. And when you do this math, a lot of things cancel out, and all you're left with is the arctangent of negative omega over omega naught. And this is the phase equation. So with these two equations, our gain equation and phase equation, we can use this to plot on our Bode plot. You can either plot these on a graphing program such as MATLAB, or you can do what we're about to do and just estimate what these graphs look like by hand. And we'll do that by looking at the parts individually. Let's take the first case. That's when omega is much less than the break frequency omega naught. When that happens, this omega squared over omega naught squared tends towards 0. So all you're left with is the square root of 1. And in this case, the gain equation simplifies to just negative 20 log base 10 of 1, which is 0 decibels. And we can write that on our gain plot somewhere in this area. And the phase is the arctangent of 0, which is also 0 degrees. And we can mark this point on our phase plot. The second case is when omega equals our break frequency omega naught. When that happens, omega squared over omega naught squared equals 1, and this thing ends up being the square root of 2. So our gain is equal to minus 20 log base 10 of the square root of 2, which is equal to minus 3 decibels. And we can estimate that point on our gain plot somewhere just below the break frequency. Now for phase, this is the arctangent of negative omega over omega naught, but those are equal, so it's just the arctangent of minus 1, which is minus 45 degrees. Now the third case is when omega is much greater than our break frequency omega naught. In this case, omega squared over omega naught squared dominates this equation. It's usually much greater than 1. So we can rewrite this as minus 20 log base 10 of just omega over omega naught. So at this point, every time omega gets 10 times bigger, the gain drops by minus 20 dB. So we can say that this produces a line with slope of minus 20 dB per decade that intercepts the 0 dB line at omega naught. So I can just write this in here, which is this green line at minus 20 dB per decade. As for the phase, as omega gets larger and larger and larger, negative omega over omega naught goes towards negative infinity, and I left off the negative accidentally, which produces a phase of minus 90 degrees. Now we have these 3 points, but what does the real function look like? For gain, I've drawn it as this yellow line, which can be approximated by 2 line segments. The first at 0 dB going to omega naught, and the second starting at omega naught and dropping off at minus 20 dB per decade. For phase, the real plot looks something like this, which is this sloping S that starts at 0 degrees and goes to minus 90. Estimating this is slightly trickier, but can be done with 3 line segments. First, you have to find the points on the graph that represent 1/10 of the break frequency and 10 times the break frequency. The first line's at 0 degrees and goes up to 1/10 of the break frequency. The next line slopes down to minus 90 degrees at 10 times the break frequency, and then it's just flat at minus 90 degrees from that point on. So now when you come across a transfer function that has a single pole, you can estimate the gain plot with 2 straight lines in this manner. And then you can also estimate the phase plot with just 3 straight lines like we've done down here. Now I know I went through this pretty fast, so if you have any questions on what I've done here, please feel free to leave a comment in the section below and I'll try to address it. So now you might have the question, how can I determine the frequency response of a transfer function of a single zero without having to go through all this math again? We can do it the same way that we did it on the video on poles and zeros at the origin, which is that we can write a transfer function that has a real zero as 1 over a real pole. So the transfer function becomes 1 divided by 1 divided by 1 plus s over omega, which is just a complicated way of writing 1 plus s over omega naught. And like we did before, we can use the fact that we're plotting this on a log-log scale Bode plot to simplify this even further. The real zero just becomes the negative of a real pole when you plot it on a Bode plot. So in that case, the gain would slope up at 20 dB per decade, and the phase would also gradually increase up to positive 90 degrees for a zero. Of course, the best way to prove this is to actually go through the math like we did with the real zero, but I'll leave that up to you if you're interested in doing that exercise. Let me summarize the rules for approximating the transfer function for a real pole or zero, just so hopefully it sinks in. The first step is to write the transfer function in one of these two forms, either the form for a pole or a zero, depending on what you're starting with. For a pole, the Bode plot can be approximated as follows. For gain, find the break frequency omega naught, then draw a straight line at 0 dB up to omega naught, and then draw a line from there down at minus 20 dB per decade. For the phase plot, locate the break frequency 10 times the break frequency and 1/10 of the break frequency. Draw a straight line at 0 degrees to 1/10 omega naught. Draw a straight line at minus 90 degrees phase, starting at 10 times omega naught and going to infinity, and then just connect the two lines. The rules for drawing a zero are similar. They're just reflected along the horizontal axis. So for the gain plot, you find omega naught, you draw a straight line at 0 dB to omega naught, and this time you slope up at 20 degrees per decade. And for phase, again, you start at 0 degrees, going up to 1/10 omega, but this time you jump up to positive 90 degrees at 10 times omega naught, and then you just connect the two straight lines. Now at one point you might find that you have a transfer function with a single pole, but you can't write it in the form here. For example, this transfer function, which is 1 over 4 plus s, which has a single pole at s equals minus 4. But you can factor out any constant gain you need in order to put the transfer function in the correct form. For example, 1/4 times 1 over 1 plus s over 4, where the first part of this is a constant gain, and the second part is a real pole where the break frequency is 4 radians per second. Of course, you can also extend this idea to a transfer function of increasing complexity by factoring out all of the individual building blocks and writing the response for each and summing them together. In the next video, I'll discuss the frequency response of a transfer function with a pair of complex poles or zeros, and then you'll have a complete set of building blocks with which you can build the frequency response of any transfer function. I know this video got complicated at times, but I appreciate you sticking through to the end, and I hope that you got something from it. I'll see you next time.